Now suppose we've applied the alternating series test and we know that our alternating series converges to some number s, but we don't know what s is and we'd like to estimate it. One way of doing this might be just to take the sum of the first n terms of the series, the nth partial sum, which we've been calling Sn, as an estimate to the sum of the series. And of course, if we do that, just like when we use Simpson's rule to estimate integrals, we'd like some control over the error in our approximation. Now, of course, if we know the nth partial sum and we know exactly what the error is, then we know what the sum of the series is. So estimating is really pointless. However, we can put bounds on the error without actually knowing exactly what the error is. So the difference between the sum of the series and the nth partial sum, s minus Sn, is called the remainder, and we denote it here by r subscript n. And of course, the absolute value of the remainder tells us exactly how far our nth partial sum is from the sum of the series. And of course, the nth partial sum might be overestimating or underestimating the sum of the series. If our series satisfies both conditions of the alternating series test, then we know it converges, and also the estimation theorem tells us that the absolute value of this remainder for the nth partial sum, the absolute value of s minus Sn, is less than or equal to the positive part of the n plus 1th term, bn plus 1. And you'll find a proof of this at the end of your notes. It's not very difficult. It's something you should certainly read through. Well, how might we use this? Suppose I want to find a partial sum approximation to the sum of the alternating harmonic series, where the error of approximation is less than 0.01. Now, here the positive part of the nth term is bn, it's 1 over n. It's positive for n greater than or equal to 1, and we've already seen that both conditions 1 and 2 of the alternating series test are satisfied. So this series certainly converges. The nth remainder, Rn, which is the sum of the series S minus the nth partial sum, by the alternating series estimation theorem, is less than or equal to the positive part of the n plus 1th term, which is 1 over n plus 1. Since the error of approximation is less than or equal to 1 over n plus 1, then I know that if 1 over n plus 1 is less than or equal to 1 over 10 squared, that the error is less than or equal to 1 over 10 squared. So if I choose an n plus 1, where 1 over n plus 1 is less than or equal to 1 over 10 squared, I'm guaranteed that the error in my approximation is less than or equal to 1 over 10 squared, which was my goal at the beginning of the problem. So I'm going to solve for an n where 1 over n plus 1 is less than or equal to 1 over 10 squared. And of course this happens if 10 squared is less than or equal to n plus 1 using cross multiplication, or if n is bigger than or equal to 101. This is going to happen. To estimate the sum of this series with an error less than or equal to 10 to the minus 2, I sum the first 101 terms of the series. That is, I take the sum from 1 to 101 of minus 1 to the n over 1 over n, the 101th partial sum. And then I know that the remainder, the absolute value of the remainder, is less than or equal to 1 over 10 squared. Obviously, this is not a partial sum that you would calculate by hand. Your computer would do that for you. And in fact, in Mathematica, we can compute the sum of this series. In fact, probably somewhere in your notes, I talk about the sum of this series. And the true value of the error here, the absolute value of the remainder, is 0.00492599, etc. And this is indeed less than 0.01, and as with Simpson's rule, we see that we're being a little bit conservative here about the error. The error is actually quite a bit less than the 1 over 10 squared. However, if we don't know what the sum of the series is, we don't know what the actual error is, but we're guaranteed that it's less than 1 over 10 squared.